Hello, everyone. Welcome to another Q&A about history of science and technology. I am not yet back in my natural habitat. I will be next week. Here we are. Well, let's see. I have a bunch of questions that came in here. Well, there's a question about combinatory logic and statistical mechanics. Well, actually, as it happens, I've been making quite a study recently of the history of statistical mechanics and thermodynamics. And maybe I could describe a little bit about that. So, I mean, the big story that led to statistical mechanics, the sort of the aggregate theory of lots of molecules and other things bouncing around, the big thing that led to that was thermodynamics, the study of kind of the dynamics of heat. And I think the thing that really drove that was in the 1700s with the invention of steam engines, which had precursors even back to antiquity, but the full steam engine that came into existence in the mid-1700s, that was a story of you take heat and you make useful mechanical work from the heat by having the steam expand and push pistons and things like this to make mechanical work. And I think people like James Watt and so on were concerned about questions like, how would you make a steam engine more efficient? What would be the, is that a possible thing to do? And maybe one possibility would be, can you have something where you just take a bunch of heat and you convert that heat into useful mechanical work? Just have something that's hot and that's all you have. Can you turn that into useful mechanical work? Now, people had tried to do that. They tried to make a, that eventually got the name of a perpetual motion machine of the second kind. Let me explain a couple of things. So there's a big question about what is heat? What a gas is made of? What happens when you heat up a gas and it expands, for example? In the 1600s, people already started talking about the idea that gases might be made of discrete atoms of some kind bouncing around. For some reason, which I need to track down, by the 1700s, that theory had really gone out of favor. And there was instead the idea that heat was some kind of fluid, a phlogiston fluid that would suffuse things and be the thing that contributed to heat. And the thing that, and so that was a thing that really dominated the 1700s. And until the mid 1800s, there was still this kind of phlogiston theory of heat. And the idea that heat was a kind of motion of discrete underlying molecules, that was an idea that really didn't come in seriously again until the mid 1800s. And I think there started to be these questions about, okay, how would we make a really efficient steam engine? Well, when you have the phlogiston theory of heat, you have all kinds of weird things that you think about making an efficient steam engine. And one of the things that was true was that there was clearly a notion of mechanical work and energy expenditure and things like that existed as you moved material things, levers and pistons and wheels and so on. You move those things around. That's clearly a form of energy usage, mechanical work, etc. Moving a thing through, moving a force through a particular distance, that's sort of almost a quintessential definition of energy. So this question of what was the relationship between heat and mechanical energy was a thing that was sort of a big thing in the early 1800s and so on, very confused. A guy called Mayer was, I think, the person who first really suggested that maybe heat is a form of energy. And maybe there's even a conservation of overall energy, that you can have energy in the form of heat, molecules individually bouncing around, or in the form of mechanical work, sort of systematic motion, but they're all just kinds of energy. And that idea became called the first principle or the first law of thermodynamics, the law of energy conservation, that says that you can have energy in the form of heat, you can have energy in the form of mechanical work, you're just trading off these energies. You can't get sort of energy from nothing. And so one of the questions was, could you have a perpetual motion machine of the first kind that violated the first law of thermodynamics and just generated energy from nothing? It was the first possibility. The second thing was, what could you really do with heat? To what extent could you take the energy that is in the form of heat and organize it into mechanical work that would push pistons and things like this. And that led to a set of principles in the the first thing I suppose that happened was the work of Sadi Carnot in the 1820s, not widely known at the time, although within a few decades became more widely known. Carnot, his interest was, how would you make a more efficient steam engine? How in general would you make a more efficient heat engine? And I suppose the big thing that he did was to have this idea that you could talk about an idealized heat engine. You didn't need to be specifically talking about the engineering of steam and iron and things like this, that you could have a theoretical abstracted heat engine and discuss its efficiency. And he kind of suggested the idea that the real way to make a heat engine was to have a hot reservoir and a cold reservoir, that you were dealing with the difference of temperatures between two different things. And by the way, I should say that the idea of temperature is something you can measure, and that different kinds of thermometers would measure the same temperature from something. That was an idea that had started, I think, in the 1600s, that there was a definite notion of temperature, and that although you might have different ways of measuring it with an alcohol thermometer or a mercury thermometer or whatever else, you're measuring the expansion of alcohol when you increase the temperature, or the expansion of mercury when you increase the temperature. And nowadays it will be an electronic device where you're measuring the increasing number of charge carriers that get promoted to the conduction band or something when the temperature goes up. But that's a thing of modern times, thermoelectric kinds of effects. Back in those times, it was mostly expansion of liquids and things that was used to measure temperature. But the idea was these different temperature measuring methods would agree. It wouldn't be the case that, oh, if you measured an iron bar, a mercury thermometer would say it was this, and an alcohol thermometer would say it was that. And if you measured the air, you get a different relative result from mercury and alcohol. No, you got the same result. There was a definite notion of temperature independent of the measuring device that you could get. And so what Carnot said was, well, it seemed like the efficiency of a heat engine would depend on the difference in temperature between the hot part of the heat engine and the cold part of the heat engine, that the story was really a motion of heat from the hot part to the cold part. It was some kind of way of making that heat systematic by somehow taking, as we would now understand it, taking all those microscopic motions of molecules and saying, there's a place where they're all very hot over here and they're all running around very fast. There's a place where they're cold here. If you connect those two together, there will be a systematic motion of molecules that will go from the hot side to the cold side. But to Carnot, it was kind of the idea of idealizing the operation of a heat engine, not in terms of the particulars of steam and so on, but just in terms of a high temperature part and a low temperature part. It's kind of amusing to read Carnot's works because he begins with this giant, I think his piece is called On the Motive Power of Heat, at least in English. It was written in French originally. It really begins with a giant pitch for the importance of steam engines. And it's like, you no longer have to use air currents, that's windmills, or animal power, that's donkeys and things, to get energy. You can use a steam engine, and a steam engine will be portable. And he quotes things like the fact that in England, he says that sort of this critical thing occurred, that coal mining had become uneconomical because it was too difficult to raise the coal and so on from the mines. But now there are steam engines, and it's 10 times more efficient to mine things. It's kind of a lesson for modern times that if there's oil in the ground, but it can take more and more effort and be more and more expensive to mine it out, and it depends on whether it's worthwhile. But that was a case where the steam engine was the thing that really apparently made sort of coal mining practical again in England, and probably eventually led to the Industrial Revolution and all kinds of things like that in England. In any case, the question of so going back to Carnot had done this idea of thermodynamics, this idea of motion and motion of heat and its relationship to mechanical work, and this idea of the need to have a hot reservoir and a cold reservoir. And what people really wondered was, if you just had the hot reservoir, you just had something that was hot, could you derive mechanical work from that? And that became this question of, could you make a perpetual motion machine of the second kind, and the second kind related to violating the second principle, the second law of thermodynamics. And that second law of thermodynamics came in different forms. A person called Clausius in the 1850s was a person who was sort of key to identifying ways to state this. But it would be things like, we just observed that heat doesn't spontaneously go from a colder body to a hotter body. If you have something that's hot and something that's cold, yes, the hot thing can make the cold thing hotter, but the cold thing can't make the hot thing hotter. The heat always flows from the hot side to the cold side, so to speak. So that was one kind of statement of the second law of thermodynamics. Another statement, let's see. There are a variety of kind of related statements of the second law about the question of under what circumstances. Yes, so the other common statement is that you can't make a perpetual motion machine of the second kind, that it's not possible to derive mechanical work purely from a single hot thing without this hot-cold difference, so to speak. In any case, between the statement of the first law, energy conservation, and the statement of the second law, which seemed like it was the same kind of thing, that was the 1860s. And then William Thomson, later Lord Kelvin, got into the act with his statements of the second law. And then James Clerk Maxwell got involved with a very nice, a sort of clear approach to talking about heat and temperature and so on. Now, at the time, nobody knew yet that molecules were a real thing. They kind of realized that the phlogiston theory wasn't making it, and that there had to be some kind of molecular theory of heat. But it wasn't really fully established what that would be, and nobody knew like what the shapes of molecules were and so on. If you look at the works of James Clerk Maxwell, a lot of what he talks about is actual molecular collisions, and he's studying the classical mechanics. Classical mechanics was kind of a big field at the time of, if you have spherical molecules and they collide, he's got all these diagrams of force vectors and so on about how the collisions work, all those kinds of things. What really happens? Then he considers the case, what if the molecules were the shapes of were sort of triangular prisms and polygonal molecules, polyhedral molecules, things like that? What would happen in these collisions? And so one of the things that Maxwell does is to derive the distribution of energies that you would expect in these collisions. And actually, it turns out it's a very general result. I was just playing with this just yesterday, and it's something where it's actually, you need very few assumptions to derive this. As soon as you have something where you imagine that pairs of things collide and they exchange some energy and then they go out again, and the total energy of the incoming particles is the same as the total energy of the outcoming particles, it's just redistributed between the particles. That fact alone, together with a minimal degree of randomness in how those collisions happens, is sufficient to give you a very specific distribution. The probability that you get a molecule of energy E falls off exponentially with E. It's the so-called Maxwell-Boltzmann distribution that was derived by Maxwell. Well, the full Maxwell-Boltzmann distribution has a factor for just counting vectors, the number of vectors of a given length. So it's a v squared e to the minus mv squared type formula. But the thing that so by the 1860s, there's kind of this idea of, oh, there's this underlying molecular structure. There's the second law of thermodynamics that tells you what you can kind of do with all these random molecules bouncing around. Then the next piece was this question about equilibrium, this question about when would a process be in equilibrium, in the sense that its properties would no longer be spontaneously changing. At least its aggregate properties would no longer be spontaneously changing. So, for example, if you have a gas rushing from one container out into the vacuum, that's not equilibrium until the gas has kind of just sort of settled itself into the vacuum or whatever. And so that was sort of the question of when you are out of equilibrium, what is the tendency of what happens? And what was realized was that the second law of thermodynamics, this law that talks about the overall features of heat and temperature and so on, really has the implication that what has to happen is that things get more random. You can't, so for example, looked at in terms of molecules, mechanical work, you have a bar of stuff and it's got a bunch of molecules in it. when you move that bar, all the molecules are moving in the same direction. When you simply heat up that bar, all the molecules are running around. They could be running around very fast, but they're running around in random directions. And so the second law basically was understood to be things tend to go from systematic to random. There tends to be a progression of things getting more random. Now, then into the scene comes Ludwig Boltzmann, who then tries to derive the second law. I should mention another important piece. Clausius had defined this quantity he calls entropy. So energy was this quantity. People like Mayer had said entropy is energy is a thing and it's conserved. And the question then was, well, is that all there is that determines how systems work, is the conservation of energy? And what Clausius said was, no, there's actually another thing. We'll call it entropy. And he had kind of a entropy. He wanted the name to sound a bit like energy, but to be about trope, transformations, the Greek word for transformation, trope, that went into entropy. So it was about kind of transformations of things. And the idea was that it would describe the way in which things could transform. And so what happened was Clausius defined the entropy to be, well, in sort of mathy notation, dq over t. Q is the heat, dq will be the difference of the heat, and T is the temperature. So entropy is basically the as you change you change a thing, you're adding heat to a thing, but you're asking at what temperature is that heat going in. So this is saying as you change the heat divided by the temperature, what result does that give you? And he defined that as being the entropy. And he said that the second law was the law that entropy quantity always increases in a closed system. That if you just have a system where there is where things are just sort of rattling around, there's no effect from the outside, that the change of let's see, I'm getting myself confused because it's the adiabatic case is the case where there's no heat coming from the outside. Isothermal would mean there's no temperature change. But I guess what's happening here is you have a change of the entropy that is associated with this sort of progressive change of both heat content and temperature. Okay, so then the next big question was, well, what is this entropy object? You know, is there some other interpretation of it, perhaps in terms of molecules? The big thing that Boltzmann suggested was this formula, which was eventually on Boltzmann's tombstone, what he wrote as S equals K log W. Later, it was more often written S equals K log capital omega. What it was the entropy is equal to some constant now called Boltzmann's constant times the logarithm of the number of states in the system. So a very weird sort of connection between microscopic counting of states in the system and the entropy quantity. But why is something like that right? I think at the time it was much less clear, although when I was just looking at a paper of Boltzmann's yesterday, and Boltzmann was actually doing quite a lot of discrete mathematics. It makes sort of Planck's achievement in 1900 of understanding black body radiation and the Bose-Einstein distribution, so the Planck spectrum, and then later Bose-Einstein statistics, makes that a little less impressive because Boltzmann was really already doing this thing where he says, let's consider something where there are just 7 possible boxes and each one has an integer number of things in it. And he was doing that as a way to kind of make real this counting of states, this S equals K log omega kind of thing. But so why should entropy, defined as this heat to temperature ratio, have anything to do with the counting of the number of states? Well, first thing to realize is if you've got n boxes, sort of n places where you can put energy, let's say, n particles, whatever else, n degrees of freedom, then the number of possible configurations of that is something like 2 to the n. So the logarithm gets rid of the 2 to the n, and it's just n times some constant. So what that logarithm is doing is saying basically how many degrees of freedom are there? So it's saying entropy is equal to some constant times the number of degrees of freedom. But also this heat quantity is kind of that heat is the sort of macroscopic version of how much energy is there in the system. Temperature is defined to be basically related to the average energy per particle. And so this heat divided by temperature thing is essentially measuring the number of particles or the number of degrees of freedom. And that's why there's a connection between kind of the entropy as defined by Boltzmann of K log omega and the entropy as defined by Clausius as dq over t. Anyway, so that was the thing Boltzmann realized in the 1860s. And then Boltzmann tried to work out if you had collisions between molecules, how would this entropy quantity, now understood microscopically, how would that entropy quantity change? And so what he was doing was then to say the entropy is equal to, if F is the number of particles of energy E, it's F log F, basically, the integral of that over energies is the entropy. And so then what Boltzmann figured out is that there is a that entropy quantity he defined as the negative of the current one is something that decreases, the H function decreases, the entropy increases with time. And so he worked that out by just working out if you have collisions of molecules and they're random collisions of molecules, then this quantity, this F log F thing that he worked out, it's just a mathematical result that causes the entropy to increase in time. Okay, well, it's a little bit weird because here's the big problem. The other big thing people thought about was reversibility. The fact is that the laws of mechanics, rigid balls bouncing off each other, they're reversible in the sense that any process that can go in one direction can equally well go in the opposite direction. Now, a little micro footnote, 1964, this phenomenon called CP violation was discovered in particle physics in the decays of the K0 meson, which is a phenomenon whereby it isn't in fact the case that every property of things is the same when time is running forwards as when time is running backwards. But it is the case that every process for which there is a forward description of the process, you can reverse the description and make a backward description of the process, though those forward and backward descriptions aren't necessarily quite the same. It's kind of like the difference between symmetric cryptography and asymmetric public key cryptography. In sort of symmetric cryptography, the encryption and decryption are the same. In public key cryptography, the thing going in the forward direction has a different key than the thing going in the backward direction. And so it is with CP violation or time reversal violation that was discovered in the early 1960s. But that's not really a relevant effect. That doesn't affect this Boltzmann result that entropy can be computed to increase based on this microscopic model. Okay, that's very weird, because how can anything increase with time if everything is symmetrical and you could just reverse the time and everything should go backwards? And in fact, this is often in textbooks, but sort of my favorite, not favorite textbook quote is, the textbook will go through and prove the H theorem and then say, but you could in fact reverse all the times, and then you would prove the opposite of the H theorem. And it says, one famous textbook, I think, ends its chapter with, this point is often puzzling to the student, as it has been to people for 100 years, but that's a different issue. So in any case, how does this actually happen? Well, people at the time of Boltzmann had all these objections to Boltzmann's result, like the reversibility objection. Another objection was that eventually any system would recur, that any system would eventually repeat its behavior. Any deterministic system would eventually repeat its behavior, although the time to do so might be exponentially long. But so this reversibility objection, it's like, how can you have proved that entropy increases when your proof would have to be able to be run in the opposite direction? And from a practical point of view, why do we observe that if you smash something, it's broken into little pieces, and it doesn't, you can readily smash things, but you can't readily sort of have a self-assembly of things to have all those pieces come together again? Why does there seem to be this kind of arrow of time that leads to increasing randomness? And I think this is something I finally understood. I sort of made a big, I almost understood it in the 1980s, and I think finally now do understand it. And it all has to do with the question of, well, there is in principle a way that you could prepare all the molecules so they'd all come together and make this very orderly thing at some point in the future. But that way of preparing it is not something that a computationally bounded observer like us can execute. That instead, we have to think about it as this process of evolution of the system is a computationally irreducible process. And so when we ask questions about what's going on, we are computationally bounded observers. We can only see certain kinds of things, and we can only prepare certain kinds of states, and they inevitably have these properties of getting increasingly random and so on. But I should explain that in the history of statistical mechanics, another big figure was Josiah Willard Gibbs, an early American physicist from the 1870s, lived until the early 1900s, worked at Yale all his life. He really tried to sort of more mathematicize this treatment of statistical mechanics and introduced this idea of ensembles, the idea of looking not just at the evolution of a particular system, but a whole collection of possible configurations of the same system. And so many results of statistical mechanics were quoted in terms of these ensembles. And that was sort of the originating idea of lots of mathematical statistical mechanics led to this idea of the partition function. The partition function is something quite that gets used in different forms in quantum field theory and things like this. So sort of a general idea. I think there was a question of here about the relationship between statistical mechanics and things like combinators. You know, the history of computation and the history of statistical mechanics have been very disjoint histories. I mean, I think I personally have been the person probably most involved in trying to bring those two traditions together. Maybe there are a few other people who were involved in the question of the thermodynamics of computation. Like John von Neumann had made the statement that every computation is necessarily dissipated, necessarily turns sort of mechanical work into heat. This turns out not to be true. A guy called Rolf Landauer argued this, that a person called Charles Bennett gave a nice example of how this fails to be true. Other people, Ed Fredkin was involved in another example of this. And the basic observation is that the way that dissipation occurs is when you make a choice and then you throw away the other choice. That's when dissipation, when sort of heat is generated. So for example, in a typical logic operation, if you say it's the or of two things, it's like we have a 1 or a 0, or a 0 or a 1, and both of those give a 1, but you don't know whether what came before that output 1 was a 1 0 or a 0 1. You can no longer reverse things. You no longer have reversibility. When you don't have reversibility, it inevitably follows that you have this kind of dissipation process going on. And so then the question is, can you make reversible logic? And the answer is just simply plainly yes. And for example, when people do quantum circuits, that's all based on reversible logic, because quantum mechanics, before you make measurements and things, is a reversible mathematical setup, or it has the same, it's why it has unitary evolution. The unitary matrix is invertible. So there was kind of this attempt to mix sort of this question of whether thermodynamics and computation mixed that way, and that was sort of one emerging thing. Then my own efforts had to do with kind of introducing this idea of computational irreducibility in the mid-1980s, 1984 or so. And I just found yesterday, actually, I'd completely forgotten this. I have a statement at the end of a paper I wrote in 1985 about origins of randomness in physical systems. I basically say whether these sort of intrinsically random processes, I say it seems likely that these intrinsically random processes are directly related to the second law of thermodynamics. And that turns out to be true. And I've now figured out a lot more detail about that path of things. But in any case, that was, but in terms of other connections between sort of computation and statistical mechanics, I don't think there really have been many. I think we're now seeing very interesting convergence of those things where we think about statistical mechanics in computational terms, and we think about the lessons of statistical mechanics of the emergence of continuum behavior and things like this as being relevant for other kinds of computational processes and thereby physical processes. Okay, let me see. We have a question here from Brady who's saying, wonders why I didn't explore chess in my paper on multi-computational games, and can I discuss the history of chess AIs? Can we design a better game somehow, and so on? The reason I didn't do study chess was because I didn't get around to it. Bright fellow at our summer school this year actually did study chess endgames in multi-computational in a multi-computational way and got some really nice results actually. So he was able to follow up on that idea. Well, let's talk about chess. Chess is a really old game, and played for a long time, different places. The sort of the theory of chess, I think by the late 1800s, early 1900s, there were an increasing number of sort of top chess players who sort of were thinking theoretically about kind of these are possible end games, we're cataloging end games, things like this. So far as I know, 1912 was the first time that anybody thought about the kind of graph of a game. So, you have a state of a game as a node, and you have that's joined to other states of the game by plays that you can make. And you can ask the question, how does the graph that you form from all possible sort of moves that you can make in the game, what is the structure of that graph? What can you say about it, and so on? And I think Ernst Zermelo was the person who worked on Zermelo-Fraenkel set theory, the sort of standard axiomatic theorem used in mathematics. He, in his talk at the International Congress of Mathematicians in 1912, had something about chess and game graphs. And he couched what he was discussing very much in terms of set theory, because that was kind of his brand, and was talking about kind of the construction of these graphs in terms of sets and so on. But in the end, he sort of mentioned, I think, some chess grandmasters and so on. In the end, it was a story of this is a way we can think systematically about chess in terms of graphs. Now, the actual graph for the full possible chess games is absurdly large. For tic-tac-toe, it's got about 5,000 different configurations of the game that can ever occur. For chess, it's 10 to the 100 or something, or much more than that can occur. And so that was kind of the sort of the early mathematicization of chess. Then I would say the first time, there had been sort of supposed chess automata, famously the Mechanical Turk, was in the 1700s, 1800s maybe, which was a very small person who was a good chess player, sitting inside a box, moving things around with magnets and playing a chess game. And that's kind of like it's artificial intelligence, where it's actually a person inside the machine, so to speak, that's doing it. The Mechanical Turk, I think it was a Turkish person who was the circus provider, so to speak, of the Mechanical Turk thing, and that was kind of an early sort of fake chess automaton. When did real ones start being talked about? Well, I know that David Champernowne and Alan Turing, who were friends at King's College, Cambridge in the 1920s, got interested in chess playing, sort of automating the game of chess and figuring out how to make kind of a machine to play chess. I don't know how far they really got with that. Then when people were looking at, Turing and friends were studying kind of the breaking of the Enigma codes during World War II, kind of that notion of you tree out all these possibilities, you look at all these possible passwords effectively, that started to feel a little bit like you try out all these possibilities in a chess game. And I think maybe that led to maybe further discussion from Turing on the possibility of machines to play chess, but he never actually implemented such a thing. So I don't know who was the first person who actually built a chess computer, but I do know at MIT in the early 60s, there was a whole lot of activity around this. A person called Richard Greenblatt was much involved in making sort of a chess machine. I think Ed Fredkin had something to do with sort of sponsoring that. In fact, Ed, I think, had for a while a prize, like a $100,000 prize for the first machine that can beat a grandmaster at chess. And I think that was initiated in the early 1960s. And so there was a bunch of activity of building essentially special purpose machines that would play chess, and which would do effectively this treeing out of possible outcomes in the game. And so the big issue was, okay, you're at this configuration of the game, let's try and look 5 moves ahead and see what possible things can happen, and which of those possibilities do we like the best, and so let's pick that particular move. But I think that was something that was done in hardware with kind of special purpose hardware that was still happening let's see, that maybe I'm getting myself off by a decade or two, because certainly in the 1980s, that was, no, that was happening in the 70s, right? That was happening in the 1970s. And then by the time, I certainly knew a bunch of these people, and one of the things that sort of turned into is the effort to build a Lisp machine. And these two companies, Symbolics Inc. and Lisp Machine Incorporated, which had all kinds of entanglements with my first company, and my SMP system, which was the sort of first, I would say, commercial sort of computer algebra symbolic computation system, was well, at least it became commercial, was written in C as opposed to Lisp. But those Lisp systems were kind of the wannabes of that world, but their original use case had been things like playing chess. So in any case, this idea of how do you look enough moves ahead, and how do you how do you sort of optimize that process? That was sort of the big issue of chess machines. Now, is it AI? Well, it's very mechanical. It's very much, let's just look these number of moves ahead, let's see what happens, et cetera, et cetera, et cetera. In the end, this Deep Blue machine from IBM in the 1990s, early 1990s, I think, which sort of did the big PR thing of winning the sort of chess championships type games. That was very much a continuation of that tradition of just, grind the game tree and look enough moves ahead and see what happens, and have good assessment schemes for figuring out kind of what counts as how much is a queen really worth? If you lose your queen, you lose a bishop, you lose this, how much is that really worth? And I think that kind of probably, interwove with things that people who were sort of the people writing all the books of chess openings and things had some sense of that, and that's probably what informed how those programs are written. Now, what's happened more recently, for example, with the game of Go, which is a simpler in terms of rules, but more difficult in terms of gameplay kind of game, that was much more difficult to automate. I remember when I was a kid, when I was like 13 years old or so, I knew the game of Go, and I thought it was kind of cool because I'm not a big game playing person, but I thought it was cool because it had such simple rules. And I thought, well, it has such simple rules, it must be easy to program it on a computer. So I had access to a very primitive computer, a machine called the Elliott 903, which had 8,000 words of 18-bit memory, so very tiny memory. But anyway, the thing that I set myself was at least to figure out when would a piece of territory in a Go board be dead. And even that was quite hard to do. You had to figure out what was enclosing what, and I did manage to figure that out. But sort of the more elaborate versions of that, I didn't manage to figure out. And kind of in part of the lesson of simple rules can lead to complicated behavior, which, a decade or so after that, I kind of realized big time. But at that time, I was still sort of bashing myself against the assumption that that wouldn't be true, and that simple rules would lead to simple behavior. But I don't really know, in the kind of very publicized, AlphaGo tournaments and things like this, don't really know what the fundamental sort of core technology that's made that work is. In machine learning, you kind of get to make a choice about which way in the game tree to go and how to choose which way to go. But it's always a subtle thing. For example, when this big Jeopardy IBM thing happened in, when was that? That must have been 2010 or so, 2009, 2010, right around the time when Wolfram Alpha came out, because we'd interacted with those guys at that time. The question was, could you answer these general knowledge questions automatically? And the part that was very easy to tell, I even wrote a blog post about this, was you feed in Jeopardy questions. I think there were a couple of 100,000 that were available on the web, and any old search engine would basically get you a page of hits on the web that contained the right answer. Somewhere on that first page of results would be, and the answer is a beaver or something. And that would, the word beaver would be on that front page. Now, the challenge was to rank those things and say, you know, which one was the actual answer? It's a beaver, as opposed to a bunch of other words. And when you looked at the actual televised, you know, grand match, you could see in the sort of runner-up answers, there were pieces of sort of disembodied text that had been retrieved and their capitalization wasn't even fixed, that were the sort of runner-up answers. So it was like taking, well, which lump of text will be the thing to surface? And that was the main thing. But the thing that turned out to be kind of the real definitive winning aspect of it was something that had nothing to do with the text retrieval, you know, AI-ish part of it. It was instead just the question of, if you're playing Jeopardy, and I'm not sure I know how to play it, you have to say, I'm going to bet on this. I'm going to assume this. I'm going to make this following very probabilistic quantitative bet. And the machine was just a lot better at doing that than a human was. A human had sort of a piece of emotional baggage that caused the human to not just use the odds, so to speak, in the optimal way. And that was kind of what tipped the final outcome. So something very much, very machine-like, very not kind of woohoo, you know, AI-like. You know, I think that with chess and Go and so on, I can't really tell you how much is kind of woohoo AI-like and how much is really very much more mechanical kinds of things of just, oh, you can tree out more steps in the game or do this or that kind of thing. I do know a chap who actually worked in my research group back in the, early 80s, early to mid 80s, was very obsessed with teaching a computer to play backgammon using neural networks at that time. And I never really understood that project, and I never really understood how hard it was or how successful or not it was. But he went on to very much develop this idea of reinforcement learning and so on, and learning from what you did and figuring out sort of how to make tests of what was going on. So in any case, that was a different direction. Let's see. The comment here, several comments here. There's a comment from Philip. Do I think it's regrettable that the history of science and technology is almost never taught? Political and social history seem absurdly dominant. Yeah, well, I don't know. I haven't been in school learning history for well, basically half a century. So I don't really know what's taught now, but I tend to agree that it is the social and political history that is much more taught, perhaps almost political and military history. When I was learning these things, it's like the battle of this happened and then this happened, and there was sort of a political forces that led to this or that happening. I think in, you know, technology has had a very important effect on human affairs. And I think sometimes the effect is not well codified in the history books, because it's something where, you know, I think back in the day when, you know, Julius Caesar was writing about his exploits, you know, I think he was writing about, you know, the army won this battle. He wasn't writing, oh, and we had this nifty idea that of making a different kind of catapult and so on. That was thought to be kind of a, in the phrase that will be used when I was growing up in England, the boffins. You know, the white-coated scientists in the back room might be making the better catapult, but that kind of wasn't part of the main swashbuckling flow of what was happening. That was all happening in the front office, where the people with you know, with the horses and swords and cannons and all those kinds of things, well, later on cannons, were operating. And I think that was this kind of this sort of infrastructure of technology development. I think while it is very critical, and I think that was one of the striking things in World War II, was that there were pieces of clear sort of technology, you know, dramatic technology events, like the dropping of the first atomic bombs, and also radar, although that was a little bit more under the radar, so to speak, in terms of what was going on. But those kinds of, I think maybe the the dropping of the atomic bombs, the building and dropping of the atomic bombs was sort of a, this is a definitive technology matters for warfare kind of moment. Of course, in reality, even in antiquity, people like Alexander the Great had really emphasized, having the best technology to win the sieges and so on in warfare. But I think it tends to be the case that people emphasize, that the technology stuff is kind of in the background relative to the more obvious kind of political forces and the redrawing of political boundaries and things like this. Yeah, Dan is also commenting here that the history of science mostly focuses on results and consequences of discoveries instead of the background of the characters behind them. Yeah, that's true. And often history of science and technology is written in a sort of heroic form in which there is a person, individual person, who, at some moment figures out some amazing thing, and, the apple falls on Isaac Newton's head, and then he has the theory of gravity. In my experience, no such story is the whole story. There may be some precipitating event or something which causes people to really think about something they weren't bothering to think about before. But usually there's at least a decade-long kind of run-up in which people find sort of the context by which things work. And often there's a great entanglement of technology and science. You think, oh, Einstein invented relativity, and that was just a sort of philosophical, scientific, mathematical thing. But in fact, this notion of simultaneity was something which was a big thing in Switzerland at the time, because they wanted the trains to run on time, and they had these electrical wires, telegraph wires and things going from one station to another. And it was like, could you really make sure that the train was arriving at this minute at this station, and what did that mean in terms of simultaneity at the next station? It was really a technology of the time type story, and that's been true over and over again, that both in terms of the technology that's necessary to make a discovery, microscopes, telescopes, electronic amplifiers, those kinds of things, the making of a discovery is something that it relies on both the technology that allows you to make the instruments, and often the ambient way of thinking that comes from the fact that technology is all around. So in today's world, the fact that we have computers all around and we have intuition about how computers work has been, at least for me, really critical in defining what happens in basic science. I will tell you one footnote to history that I just learned. I mentioned Josiah Willard Gibbs, kind of pioneer, Yale University pioneer of statistical mechanics in the late 1800s. Here's a piece of strange history. He didn't have very many students. One of them was a guy called Lee de Forest, who was a kind of an inventor, and who, in the traditional heroic version, he just sort of invented stuff. Well, actually, he had a physics PhD, and he'd studied a bunch of physics. And it wasn't just, he'll just pull these inventions out of thin air. But one of the things he invented was the triode, the vacuum tube amplifier or switch, which was critical to early radio and things like this, or to electronic amplification. And it's an interesting fact that he was a graduate student in physics of Gibbs. And so there was a sort of relationship between the statistical mechanics and the origination of vacuum tube technology and triodes and so on, through that link of a slightly colorful inventor kind of person. But yeah, I think one of the things that tends to happen is that there's the story of how discoveries get made is often kind of complicated. It is easier to make the heroic version of, this is the story. And one thing that doesn't help is that sometimes even the people involved in discoveries will heroicize them after the fact. And something which was, oh, well, actually I was, working for 20 years on this, and I, got my PhD in this, and I'd studied that, and I'd written extensively about this and that, gets conflated into, oh, I just had this great idea one day, partly because I think people in their own minds remember that moment more than they remember the long run up to it, and partly just because it makes a better story. And, the oft-told story that, Albert Einstein was a mere patent clerk toiling away in the Bern patent office when he invented relativity. Well, footnote, he got a PhD in physics, and the Bern patent office was kind of the Silicon Valley of its day. So, that makes it a little bit less kind of just the poor kind of unwanted kind of garage inventor who had no sort of no background in anything. That isn't usually the picture, and usually the full picture is a much more intertwined with the evolution of ideas and technology of the time and so on. And the stories are interesting. I mean, I've tried to tell some of them. I have this book, Idea Makers, which has a collection of a bunch of these stories that I tried to untangle, and I've untangled some more since then. But yeah, the stories are great if they're told, but they tend not to be one sentence type stories. They tend not to be just the another one like this is Ramanujan telling J.H. Hardy when Ramanujan got fed up with Hardy saying, but how did you get this mathematical result? How do you show a proof of that? When Ramanujan didn't have any proof because he was doing essentially experimental mathematics. And he told Hardy, well, these things come to me from the goddess so-and-so in my dreams, which I'm sure was just a joke. And it was just, and yet that gets repeated with great kind of seriousness as kind of Ramanujan's source of inspiration, when the true answer, I think, is that he was a good calculator and could actually work out all these decimal digits and work out all these series expansions and so on, and then notice patterns and such like. But that's a more difficult story to tell. Let's see. Well, the question from Universe Within here is, in the history of science, have you ever seen something really unexpected? Someone pulling something out of their hat with no prior experience? Let me think about that question. I'm thinking of so many examples where that's not the case. The invention of the microscope. Well, there were lens grinders and they were doing detailed things. The invention of let me think about that for a second. Well, I mean, there are things that, yeah, I mean, I don't know enough about like the discovery of penicillin by Fleming and so on. He was a microbiologist, and yes, he noticed that this mold growing on this thing inhibited the growth of bacteria, but you had to be growing bacteria on a plate, and had to know what the bacteria looked like. And the most difficult thing often is that you know too much, and so when you observe something that's unexpected, you just try and ram the unexpected thing into the stuff you already know, and then conclude that there's nothing new, and you fail to make a discovery. That's a much more common thing than that you make an uncontextualized discovery. We just say this is an amazing thing, and it doesn't, it doesn't come with any context. Because usually discoveries made with no context are tough. I mean, I'm trying to think about ones that, there were ones that were surprising. Hubble's discovery of the expansion of the universe, but I mean, he was looking with a telescope at spectra of stars, galaxies, and so it was, that was not a, it's kind of like you're looking at something, and the trick is to not ignore it. When pulsars were discovered in 1968, the person, Jocelyn Bell, I guess, who was sort of on duty paying attention to the radio telescope, made the correct thing of don't ignore the fact that it's going beep, beep, beep at a, at a fixed frequency. And, that could easily have been, oh, it must be an instrument failure of some kind. Nothing can do that. Let's just ignore it. That was important to not come to that conclusion. So I think avoiding failing to discover things is a more common issue. And I'm really having a hard time thinking of something where sort of completely uncontextualized, something just sort of was noticed by somebody who wasn't even looking anywhere near that area. I mean, there are certainly effects. I mean, there are plenty of effects in biology, among other places, where it's you have to really be paying it. You have to come up with something which is not. You have to be capable of absorbing something which you didn't already know. And I'm afraid that's one of the things that is very often missing in research science is that ability. People don't have the confidence to see something that they didn't expect to see. I know, for example, in fluid dynamics, one of the things that I predicted was that there's a certain repeatability to apparently random flow patterns in fluid dynamics. And I asked a lot of fluid experimentalists, this is now 25 years ago or more, I said, have you ever seen this? And some of them said, well, now that you mention it, yeah, we kind of have seen that. But we never put it in papers because it was so weird that nobody would have believed it. Well, okay, that's how you miss a big phenomenon, is it's so weird that nobody would believe it. And so that, I think that's a big challenge. I think, let's see. Right, as Dan is commenting, a surprising event is when someone is an expert in field A somehow finds a connection with field B and makes a discovery in field B. That's happened many, many times. It's happened particularly between physics and other fields. And I myself have tried to push this a certain amount between a variety of different fields. But it's a general thing that when one field has developed a sort of conceptual ideas and formalism and so on that goes a certain distance, it's to then, it's almost like the thermodynamic case, that the thing goes from the hotter area to the colder area. You're sort of moving ideas from the hotter field to the colder field, so to speak. One thing I was just thinking about recently, and I need to track down more of this history, when the digital structure of DNA was identified by Jim Watson and Francis Crick in 1953, digital information was a new kind of thing. There were computers, the ENIAC, 1946, things like that. There were electronic tabulating machines, things like this. But this idea of things like computer memory and the idea of remembering digital information was very new. And I kind of do wonder what the relationship was between this sort of notion of digital information that we now knew could be stored in large-scale forms in what were then, first it was punch cards, and that was from much earlier, but by that time it was kind of more in digital computers, how that affected the ability to make the discovery that there was digital information in DNA. Again, it was one of these things where there was a certain contextualization from the ambient technology situation to allow one to get to this place where you could talk about something at a purely scientific level. Parker is commenting, I feel like Einstein's thought experiments were really up there, like how the thing following a beam of light and so on. Yeah, I think, Einstein was in some ways a philosopher, in a sense, more than a traditional physicist, because traditional physicists had really had the point of view, Newton laid down these laws of motion. It is our job to go and work out with calculus what the consequences of these are. And that was a very large part of physics, whether it was in fluid dynamics or rigid body mechanics or whatever else. And this idea of let's just philosophically think about what must happen if, thought experiment XYZ was something rather different from what had traditionally been done, I think, by the physicists of the day. It's something, that kind of methodology of the sort of the philosophical thinking things through thing is something I must say I've taken to doing quite a lot of. And we have a very interesting kind of strange sort of pincer situation where we have on the one hand kind of philosophical thinking about the, things, and on the other hand, computer experiments. And between those two things, that's where most of the innovations that I've been able to make recently have come from, is kind of interweaving kind of the big strategic philosophical points and realizations with let's just run it on a computer and see what happens, and develop a sort of empirical intuition from that, along with kind of conceptual intuition from thinking about things at a sort of philosophical level. So I think that's but yes, that's this idea that you can kind of think about things philosophically at some level and make thought experiments and deduce things just from sort of that intuitive stack. You have to have a certain amount of confidence to be able to do that, because it's a lot easier to know you got the right answer if you're building step by step by step with math formulas and things than to say, I'm going to make this intuitive jump from here to there. Do I get to the right answer? I mean, I must say that for myself, I think I've developed a reasonably good intuition for some things, but the way I know that I know what I'm talking about is I do computer experiments. And often those experiments don't agree precisely with my initial intuition. And so that means that I'm kind of, I have this kind of aphorism: the computational animals are smarter than we are, so to speak. They always do things we don't expect. Maybe our principle of computational equivalence should make that aphorism really be: the computational animals are just as smart as we are. But it certainly feels like they're smarter than us, because we don't expect, we expect to be able to figure out what's happening, and we can't. So a question here from Parker, or why does our intuition even work? Actually, talking of which, hold on just 1 second, guys. I will be right back with you. Oh, again, I'm in a place where if I don't have some water, I will croak out totally. Anyway, we were talking about intuition, and the value of intuition, and whether it's underrated in science, and why does it even work. I think intuition is about, we are sort of connecting patterns of things together. There's something that we see this, it's kind of like something else we've already seen. It's kind of like it has to work this way. In a sense, typical machine learning systems they're pretty good on intuition. That is, they're able to sort of extrapolate from, I think this video is going to do this in the next few frames. That's something that's very much a sort of intuition type story of, we've got this kind of conceptual framework and we're fitting things into that framework. We've kind of got this, and we see this in machine learning systems and so on, that it's kind of like, can we fit this thing approximately with the thing we've already seen? And that's kind of the story, it seems, for intuition. I think that the question of really, it's one might think of it in terms of machine learning as some kind of encoding function. The question of, can you really translate from the intuition of physics to the intuition of biology or something like that? That's an interesting thing. And another question is, each different field has a different kind of pattern of intuition. The kinds of reasoning that work in economics are different from the kinds of reasoning that work in physics or in mathematics or whatever else. And I think that's another thing that's always a challenge for people who are kind of making the jump from field A to field B. They both get a lot of extra power from the intuition of field A, but if they land in field B and they need the intuition of field B, that's often not such an easy thing to get. So let's see, there's a question from RBS. Will we ever get a philosophical programming language? Oh, I hope so. I mean, in the following sense, maybe just in terms of words, back in the 1600s, it was a big thing to try and make philosophical languages. People, the language of scholarship had been Latin for a couple of thousand years, and well, mostly with maybe an Arab sort of diversion in the Middle Ages, but no, in large measure, sort of the language of at least one strand of scholarship had been Latin. By the 1600s, people were like, oh, we should be writing in French or German or English or whatever else. And so people were looking for, is there a way we can universalize knowledge before it sort of fragments into all these seemingly different languages and so on? And that was part of the motivation of people like Leibniz for mathematical notation, was to have an internationalized version of the system of describing mathematics. That's worked out really well. there really is an international mathematical notation. There's just one for our whole planet, so to speak. It's not the case that, even in times when for many years, the main scientific developments of a country was separated from the rest of the world, it isn't the case that it developed its own math notation. No, that's almost completely true. I mean, there's some stuff, I suppose, in the Soviet Union that a few things where the abbreviations for trigonometric functions are slightly different, and a few bits and pieces like that, but that's minority issue. Really, the bulk of it is very much the same. But at that same time, in the 1600s, there was kind of this idea that one should find a way to describe things in the world in a purely sort of philosophical form, devoid of the details of particular human languages. So there were a bunch of developments along these lines. Leibniz did some of that with his Characteristica Universalis. There had been a person called John Wilkins, who was a British guy who, let's see, an essay concerning a real character, I think was its title, something like that. It's a big, thick book that attempts to define a kind of philosophical language, a language that has kind of a symbolic representation of things in the world. So it's rather charming to see the kind of categories that are relevant. I mean, kind of the thesaurus-like categories relevant at the time. There's an awful lot of stuff about death, and there's an awful lot of stuff, all the different ways to die are very much enumerated. There's stuff about, foods and things are very different from today. There's much less about technology. And there's a certain amount about kind of human affairs, and there's a bunch about theology. And in fact, the thing that at the time, it was not very clear to people, there's kind of the words, the structure of the words, then there's the way you write the words, the kind of morphology, the character you use. And in the case of Wilkins's work, he basically did the whole stack. So, in the end, his peak sort of demo was writing the Lord's Prayer in his artificial language, in his philosophical language. But it's very bizarre because it's written in these weird runic characters, in addition to being written with different words and et cetera, et cetera, et cetera. But that was a big push in the 1600s to develop this kind of philosophical language. It died after that. People didn't try again. Late 1800s, there were a few efforts. Esperanto was an example in the late 1800s. That was an example of an artificial language which was intended to be sort of I think it was called an auxiliary language, something where sort of, if there was a person, the Lithuanian met the person from the Basque country or something, and they had no common language. What would they speak? Well, maybe they should speak Esperanto, and then they'd be able to understand each other. That was kind of the idea. A person called Zamenhof, Polish chap, was the person who originated that, and Esperanto was intended to be sort of a simplified language that would take its words from kind of the generic European melting pot of words and would have no irregular verbs and things like this. It was somewhat successful. I mean, it was, I know, I was back when I was a kid at Heathrow Airport in London, for example, there was still signage that was up in multiple languages, but one of those languages was Esperanto. And that signage finally got taken down maybe 20 years ago, 25 years ago. It's kind of sad. And the total number of books in Esperanto is some number of thousands. It's not millions, and it's nothing like the tens of millions in English. And there were a number of other efforts to make these kind of artificial languages. I mean, there have been more recent ones. The two kind of extreme cases, they're both interesting. One is Ithquil by John Chiada, which is a language which attempts to be the biggest language you can imagine, where you take kind of all of the kinds of tense structures and all these constructions from all the different human languages, and you meld it together in one language. That's kind of one extreme case, where I think it's fair to say that even the creator of the language can't really speak the language, but it's a language which maybe if you could speak it, you would be able to express things in a very rich way. The sort of alternative extreme is a language called Tokipona by Sonja Lang, I think, which is a language which attempts to be as minimal as possible with only 300 words. And so you have to kind of circumlocute your way to different kinds of concepts. But this idea of sort of having a language that represents everyday kinds of discourse is an interesting idea, something relevant for writing, computational contracts where you want to write about the world, not in legalese, but in something that computers can understand. I've been pretty interested in this stuff. Kind of the phrase I've used, which I'm not wholly happy with, is symbolic discourse language to describe this kind of thing one's trying to create. I hope that it won't be very long before we will have such a thing, but we'll see. Depends on all the other pieces of work and distractions and things about running companies and so on that I need to do in the intervening time, and all the different things that come in from science, and the extent to which we have this tremendously fertile period of sort of scientific investigation right now. Well, let's see. We probably have to wrap up in a moment here, but maybe one or two more. So a question here, interesting, from John. What do you think about the relationship of philosophical thinking and experimental mathematics, the limits of reason and the limits of Turing machines? Well, I think that philosophy is kind of getting a bigger picture of the way things are, and whether those things are things about sort of the human world, or things about the natural world, or things about the mathematical world. It's kind of zooming out and getting bigger pictures and making deductions that are not deductions for the specifics of those particular areas, but general deductions about things of that kind. And I think that experimental mathematics is another source of, it's a sort of another world about which you can have sort of philosophical thoughts. And I think the thing that, if we look back to the, oldest kinds of philosophical traditions, people like Aristotle were sort of trying to describe things in the world and bring them to a human level. Why does something fall to the center of the earth? Because it has it sort of wants to do that. So that's sort of a humanization of that idea. And I think a lot of what the sort of the science ends up being at that time, and it was then considered to be natural philosophy, was to take what we observe in the world and try and sort of connect it to human ways of thinking about things. Now, sort of a different branch was the development of logic, where Aristotle was taking kind of the arguments that humans make that seem to just follow one from another in a sort of necessary way, and making kind of a formal structure that was independent of the particulars of the arguments that were being made, whether it was about going to war or whether it was going to rain tomorrow, and being able to make statements about P and Q. He didn't call them P and Q yet, but being able to make statements based on the structure, the syllogistic structure, the syllogisms of things. All men are mortal, Socrates is a man, therefore Socrates is mortal. It doesn't have to be, it's let's see, a salmon is a fish, fishes swim, therefore salmon swim. That's the structure of that thing, and you can feed in all these different kinds of particulars and still have the same structure. But I think that's the way I would view it. Now, the question of kind of the limits of what we can think about versus the limits of what we can have computation do. Well, in our sort of theory of physics, in the end, our universe is computational all the way down. So in the end, what we can do in our universe is what can be done with computation. But it's a slightly more subtle story, because what we can sense what we can take out of our universe with the senses that we have, with the computational boundedness of us as human observers, that's a much different set of things. We don't get to go down and look at the atoms of space and look at the full structure of the Rulliad of all possible computations. We are stuck sampling a tiny piece of the Rulliad in a computationally bounded kind of way. And at that level, we observe certain things about the universe, and it's not the whole story in some sense. It's the whole story is a story that is almost an unstory, because it's a story that is a necessary story. It's a story that has no particulars in it. It's a story that is sort of all framework and nothing else. But everything is ultimately just a piece of that whole framework. And so I think when we talk about sort of the limits of computation, the ultimate computation as done by the universe has a certain structure that's all about that can be thought of in terms of Turing machines, though that's not a particularly fertile way to think about it, but you could in principle think about it that way. You could in principle convert the actual computations the universe does to their equivalent Turing machine computations. So that's one sort of level. The other level is, what can us humans take out of that? And another question is what, and so I think the answer here is that the parts of the universe that are of any interest to us, because they're parts that we're sensitive to, are just the parts that we get to extract. So it's not quite the case that, so the parts that are accessible to us humans and about which we can have what you might describe as philosophical thinking rather than computational grinding, those parts are, you might say, well, they're only a small part because that's just the stuff we humans could deal with. But actually, that's the only part that we humans sort of care about out of this whole sort of mass of possibilities that exists in the Rulliad. So, I mean, now, footnote to all of that is the fact that the Rulliad is this entangled limit of all possible computations is a definite statement. It could be hypercomputations. When we have a Turing machine, simple model of computation, and we say, let's run the Turing machine for a really long time. Okay, let's ask the question, what will the Turing machine do after an infinite time? The halting problem. Does it eventually halt, or will it keep going forever? That's not a question that we can in general answer in finite time. We can't convert what would take a Turing machine in infinite time to something we can answer in finite time. But we can always imagine that we have an oracle for a Turing machine where it just is set up to be the case that you just ask it, does this Turing machine halt or not? Just says yes or no. We don't say how it works. We don't build it out of Turing machines, but it's just a thing that exists. So if we believe such things exist, then we are talking not about the Rulliad of all possible sort of Turing machine level computations, but about the hyper-Rulliad, which is kind of a thing that contains these hypercomputations. I don't think that, I think the one fact that is a contingent fact about our world is that we live in the Rulliad and not in the hyper-Rulliad. But it sort of doesn't make much difference, because from the Rulliad, there is an event horizon. We don't get to have causal effects from either from the Rulliad to the hyper-Rulliad or from the hyper-Rulliad to the Rulliad. These two things are separated in actually very much the same way that a black hole might be separated by its event horizon from the rest of the universe. And what's happening in there, the fate of the civilization that got crushed with the star that made this black hole is something quite separate and independent and invisible to the outside part of the universe. And so it is with the hyper-Rulliad versus the Rulliad. So, yeah, well, let's see. I think there's a question here from Universal Comment about in the multi-computational paradigm, which areas am I most excited to redefine the history of? Saying, I'm excited to see you redefine the history of natural selection. Well, interesting. I might actually be having a conversation about that with somebody just today. She'll see. All right, and let me just see if there's one more question I can try and address for this time, and then we should wrap it up for now. Let's see. Building Future has made the comment, it seems that in the history of science and technology, that the hard research is usually kept out of the public eye. Has it been beneficial or overwhelming having our work open to the public, live streamed and so on? It's been interesting. It's been great, actually. It's really made it all more fun, and I hope been useful for the world. Why is most research sort of done behind closed doors? It's partly because people think that it's so technical nobody will understand, but also it's partly for, I would say, reasons like the actual doing of research involves many mistakes being made, and people don't have the confidence to be out there in public making mistakes. That's one thing. Another thing is many areas of research are deeply competitive, and people are like, I wouldn't want to put that out there because my competitor would get it instead. And so that's, I think those are kind of some of the driving forces there. And I think, for me, my efforts to sort of explain things in a way that is even worth live streaming, because it's not so unbelievably, drowning in technicality and so on, and drowning in detail. Even the effort to get things to the point where it is not absurd to do that is a worthwhile effort in helping me to understand sort of how things work better. So that's been a win. It's also been terrific to have people actually make suggestions and comments in real time. That's very, very helpful. It's, I would say, much more helpful than, you write a paper, you send it into an academic journal, and somebody says, oh, you didn't reference my works enough. And so, except they won't say my works because it's all supposed to be anonymous, which is a very big mistake, but that's a different issue. And it all sort of bounces around in that way. It's much better to have something where somebody says on some live stream we're doing, wait a minute, guys, have you thought about this or that? That's a much more effective kind of review loop than something long after the fact. You wrote the thing and then somebody is sort of complaining about something where they didn't really understand what you were talking about either. So yes, I think it's been, I've done it in different ways. When I spent a decade in the 1990s writing my big book, A New Kind of Science, I did find it rather overwhelming to interact with people at the beginning of that, because I just got so many questions asked, and people were always asking these questions, and I was like, oh, well, I should investigate that. And then I realized that if I were to investigate all these things, I would never be able to make sort of progress on the actual project that I wanted to do. So I kind of closed down and started just doing my project and not interacting with the outside world. But I would say that had live streaming been a thing at the time, it would have been great. It would have been really, I think I probably would have gotten that project finished maybe 4 years earlier than I did if I'd had the opportunity to kind of had the forcing function of explaining myself, and had kind of the enthusiasm, the sort of extra energy from kind of sharing it with people in the outside world. That would have been a very energizing kind of thing. It is an interesting question. I know I get inquiries from time to time from academics and so on saying, how can we live stream our stuff too? And it's like the basic answer is, well, it's technically very easy. And the main issue is you just have to be confident enough to realize that you're going to do this. It's going to be completely unscripted, and what's going to happen is going to happen. And yes, there are going to be things that get messed up. There are going to be things where you follow some direction and you realize after half an hour of talking about it, it's all nonsense. These things are going to happen. And it's something where, if you take the point of view that you're not trying to show off, you're just trying to share things with people, then it's kind of a good thing. And but I think for many people, many scientists and so on, the idea that you think in public is a very bizarre idea. And it's one that I suppose, I've kind of developed into that idea because I've been CEOing a company for 35 years now. And my approach to that involves a lot of kind of thinking in public, because I found that a very good way to kind of get input from different people, and also to have people kind of understand and buy into decisions that get made, because they were there and they could see what happened and they could see why that decision was made. It doesn't just seem like this thing that's coming from on high or whatever else of we should do this. It's like they understood what the thinking that was behind that decision actually was. All right. Well, we should wrap up here for today. And I look forward to being with you again. I think I will be doing a science and technology Q&A for kids and others on Friday, although it might be in a slightly even more exotic location. Otherwise, we'll be back next week. And I think we have for some other kinds of day job, software design, and other live CEOing kinds of live streams coming up. So, well, thanks for joining me, and see you another time. Bye for now.